Hello, all. Can you hear me?
Yes, bro.
Good. Let's wait a minute and we'll begin. So someone has asked to take author notes. I'm going to have to decline because we found that sometimes when we turn on author, then Zoom's recording fails. And so at least one of the lectures didn't get recorded because of author. So I apologize, but I can't take, but I'm uh, going to have to decline the author request. All right, so I'll wait till we have a couple more people in class. We have 98. And let's begin, right? So welcome to this next lecture on sequence-to-sequence models on basically recurrent neural networks. But specifically, we're going to be looking at sequence-to-sequence models. And the topic we'll be considering is connectionist temporal classification. So what is sequence-to-sequence model? Where you have a network where an entire sequence goes in and the output is also a sequence. And we saw that we could use recurrent networks for this. So in the example of speech recognition, speech goes in, but speech is actually a sequence of feature vectors, and a word sequence comes out. Or in machine translation, a sequence of English words would go in, a sequence of French words would come out. Or in a dialogue system, the user statement goes in, it's a sequence of words, the system response, which is also a sequence of words, comes out, and so on. So in each of these examples, what you will observe is that the length of the input sequence need not be the same as the length of the output sequence. And so in general, this length need not be the same as this length. And even there, we can identify two different settings. The first is where there's some kind of an order correspondence between the input and the output, like in the case of speech recognition, where the order in which these vectors occur is strictly the same as the order in which these symbols come out. So I corresponds to the initial portion of this input, 8 corresponds to the next portion, and so on. But you can have other situations like machine translation, where what goes in is I ate an apple. And if you translate it to German, one possible translation is Ich habe einen Apfel gegessen. And then if you look at this, I corresponds to Ich, but ate actually splits into habe and gegessen. And an is einen, apple is Apfel. So there isn't an extra strict order correspondence between the input and the output. Or if you had a dialogue system, the input could be my system is blank, and the system comes back with, please check if your computer is plugged in. The input and the output seem completely unrelated. But these are all examples of sequence-to-sequence modeling. And specifically, the one that we considered in the last class and that we will continue to consider today is the first situation where you have an order correspondence between the input and the output. Are these distinctions, is the notion of sequence-to-sequence modeling clear to you folks? And are the distinctions I'm making also clear? Yes or no? So I get a single yes. Okay, I'll assume we got it, right? So, all right. And so we're going to look at the order aligned, but not necessarily time synchronous sequence conversion, like in speech recognition. Here, the input and the output sequences happen in the same order. And the outputs are intermittent, but they can be aligned against the input. So here, the two problems that we'd have to address are how do we perform inference on such a model, and how do we train such models? Now, for inference, we saw a solution in the last class. We'll expand on this further towards the end of this lecture. But what we spent most time on was training. And now, in the simplest case, we saw that your training data could consist of inputs and the output sequences where the alignment between the output and the input was given, in which case you would know exactly when to read the outputs out of this recurrent network, and then you could compute the divergence just at those time instants. And we said that this is actually leaving something behind, it's dropping something. which we could use. And what did we say? And what was that? What was it that we could exploit that this is not done? Anyone remember? Anyone, guys? What was this? I'll wait for an answer. We are ignoring the fact that the network is also generating outputs at these times. And so we could exploit that by assuming that each of these symbols is actually smeared across the entire duration of the input, which ends at the symbol. And in doing this, what we have done is we've converted an output that was intermittent to an output that actually had a one-to-one correspondence with the input. And then once we did that, then we could actually compute local divergences at each time. The overall divergence could be the sum of all the local divergences. And specifically, we saw that at each time, if we chose to consider a cross entropy or a KL divergence as a loss, then the local divergence at each time is simply going to be the negative of the log of the probability assigned to the target symbol. So here, it would be the log of the probability assigned to B, right? And so this we would sum over the entire sequence, and that's going to be an overall divergence. And once we did this, then we could actually compute the derivative of this divergence with respect to each of the outputs. And for any specific output, like over here, we saw that if we wanted the derivative of the overall divergence with respect to the output of the network here, that's simply going to be, since that divergence only computes the log of the probability of the target symbol, which is B over here. So the derivative is going to be be 0 for all the symbols except the target symbol. And for the target symbol itself, it's just going to be the derivative of minus log y, which is minus 1 over the probability assigned to the target symbol. So do you folks remember this? Both this and this. So give me some thumbs up so I can wait for 20 or 30 of those before I continue. Do you remember this? Yes, no? Okay. And so this is what we did. And then once we did that, we could train the model. The problem, of course, was that the alignment was not provided in most real situations. You'd only get the sequence of output symbols, but you don't have timing information telling you where the outputs were generated. And so in this case, how did we say we could deal with the problem? When the symbols are given, but no information about where they must be output. How did we deal with this in the last class? Anybody remember? How did we deal with this? DFS? Repeat the target values, except you don't know where the target values are to be output. So what were we missing? We were missing the alignment, right? And so we said we could guess the alignment. And so we said we could come up with an initial guess. We could train the model using this initial alignments. And then once you have a model, you could use the model itself to try to align the output symbol to the symbol sequence to the input symbol sequence, which would give you an improved alignment. And then the improved alignment could be used to retrain the model, and you could cycle through this. Does everybody remember this? Do you remember this? Yes or no? Can I get a few more yeses? So, I know that you guys are engaged. All right, thank you. And so this was fine. Now, what did we say the problem was with the setup? What was the problem? Anyone? Does anyone remember why this could be an issue? Anybody? Okay. Repeated symbols. Any other guesses? Initialization. So, well, guess what? There's a poll, and you can tell me your opinions on the poll. That's right, Felix. Okay, 10 seconds, guys. All right, let me stop this. Here's what you guys thought. Should we just, here, we'll handle it. Okay. So anyway, what is the answer to the first question? True or false? Second one, true, right? Both of them are true. And the problem, as somebody pointed out, is that this approach is heavily dependent on the initial alignment, and so it's prone to local optima. And so there's an alternate solution. We try not to commit to any alignment during any pass. So, when we were talking about training without alignment, we considered two possible options. One was to guess the alignment. The other is to consider all possible alignments, and this is what we'll look at today. Now, again, remember how we went about determining the alignment. If you were given the symbol sequence, target output sequence, then the network itself, given a current model, would compute compute probabilities for every symbol in the vocabulary at every time. Then you would pull out the rows of this table corresponding to each of these symbols and construct a reduced table where if a symbol occurred multiple times, you inserted it, the corresponding row multiple times in the table. And what was the benefit of building this table? Anybody remember that? What was the benefit of building this reduced table? Anyone? Why did we want to do this? To use the Viterbi algo, right? But there was something more even before the Viterbi algo. What was it? It made sure that you could get valid alignments. You're forcing the order, right? And so if you took any path from here to here, following the rules of always right or diagonally down, whatever path you got was guaranteed to be an alignment. And so what we were doing over here was picking the most likely alignment from the set of all possible alignments and then using that to update the model. Now, the problem here is that in the initial stages of training, the model is going to be really poor. And so when the model is poor, do you expect this alignment to be reasonable? Or are you more likely to get something that's nonsensical than right? What do you think? Especially when you're initializing the model. It's most likely going to be nonsensical, right? And so this means that you're starting off from a really bad alignment, and because the alignment is key to defining the divergence itself, you could end up in really poor optimum. So instead of committing to the single best estimated alignment, let's look at it differently. The fact is that once you compose this graph, there are many paths through this graph. And so if you randomly sample the path through this graph, you could get anyone. You could get maybe this guy, right? And maybe you would get this path, or you'd get this path. And depending on, and if each of these paths has its own probability. So instead of randomly sampling a path, what we were doing was picking only the most likely path and working with the most likely path to train the model. But then if you were to consider all possible paths, every path through this graph has a probability. So if each of these dots represents a path through the graph, each of these paths has a probability. And what we were doing was picking just the most likely path, the path with the highest probability, and working off just this guy, right? And this guy could be wrong. So given that I'm taking this view of it, that there's a probability distribution over paths. And what we were doing earlier was just picking the most likely path. Can you guys suggest to me what an alternative would be from just this view? I'm sure most of you can give me an answer immediately as soon as I say this. What would it be? Sample random path. Beautiful. Alternately? Daniel, that's a very nice answer. Alternately, what else could it do? Anyone else? We could try all. Alistair, that's actually the right answer. What we can do is this. Instead of selecting only the most likely alignment, use the expected value, the average over all possible alignments. And I want you to remember that the probability, the divergence for any given alignment is simply minus of the sum over time of the log of the probability assigned to the symbol at that, of the probability assigned to the symbol on the best path at that time. So this is what the divergence was for any given path. So it was going to be minus log probability of this guy, plus minus log probability of this guy, plus minus log probability of this guy, and so on. So this is what the divergence was for any given path. Right? You remember this? Yes, no? Come on, guys. Right? So this is easy. We know this. And instead of just considering the top best path, why don't I take the statistical expectation, the average over all paths? And when I take the average over all paths, I'm basically taking the expectation over all paths of the loss for the path. And the loss for any path is simply going to be minus of the sum over time of the log of the probabilities of the symbols on the path. So is this equation making sense? When I'm saying that I'm taking the expectation over all paths. And can you tell me how I can simplify this? One-step simplification. What can I do? Mean? I can take the expectation inside, can I not? Because it's the sum, the expectation of a sum is the sum of an expectation. The average of a sum is the sum of averages, right? And so I can do that. And anyway, you guys are going to tell me, right? Yeah. Okay. 10 seconds, guys. All right, let me stop this right here. And what's the answer to the first question? True or false? First one, true. Second one, true or false? False, right? When you're training this, we are not explicitly determining an alignment. We're summing over all possible alignments. And so it's true and false. And so here's what we are going to do. And we're going to move the expectation inside. And so what this makes things very, very simple. This is the minus of the sum over all time of the expected value of the log probability of the symbol at each time. So what exactly is this term over here? I'm going over time. That's the outer sum. There's a minus outside, right? Then over time, I'm going down each path. And if I going down each column. In each column, I have 4 values, which are the probabilities of the symbol for the row at that time, right? And so I'm computing the logs of these guys, and I'm taking the average of these logs. Now, when I take the average, it's not just, I'm not just summing them and dividing them by 4. It's the weighted average because it's an expectation. So each term is multiplied by a probability. And can anybody guess what this probability term is over here? Anyone? Can you guess what this probability term is? Wait a couple of seconds. Pardon me? Hey, Jeffrey?
Is it the entry in the box?
It's not the entry.
Not the entry. My guess is that it must be, I guess, one of the lines, maybe. It's the lines between the boxes.
No, so let me explain. Can anybody else want to take a guess? Anybody else want to take a guess? If not, let me tell you, right? So this guy here is, so let's consider this row, this column, right? This term for this first box over here is going to be the probability that if I randomly sampled an alignment from this graph, that alignment would go through this node. That makes sense? If I randomly sampled it, my alignment can go anyhow, right? Some of those alignments are going to go to this node. So what is the probability that a randomly sampled alignment is going to go through this node? That is this guy. And so when I go down the column, each log term is multiplied by the probability that that node itself is going to end up on an alignment. And so here I have 4 nodes. So the sum of this term for each of those 4 nodes must sum to 1. That making sense? Yes or no? Okay. And so that's what it is. And so here we've simplified the whole thing. This guy here is the probability that when I align this input to this symbol sequence to the input, that alignment will go through the node. Basically, if I randomly sample a path through this graph, this is the probability that that path will go through this node. So for each node, I'm multiplying the log probability at that node by the probability of the node itself being on the graph, being on the path. So that means we want to compute this guy in order to be able to compute the divergence. You guys good with this so far? That this is key? Yes, no? Yes, okay, so good. Now, what is the probability that a randomly sampled path is going to go through this node? That is going to be proportional to the total probability of all paths through the graph that go through this node. Is that making sense? The probability that a randomly sampled path goes through this node is going to be proportional to the total probability of all paths that go through the node. Basically, the total probability of this portion of the graph, where every single path through this portion of the graph goes through this node. Making sense? And so this is what we're going to have to compute. But then again, it's a probability of an entire graph, right? So how do we compute it? To do that, I'm going to decompose it into 2 parts. The first is the portion of the graph that leads to this node. And the second is the portion of the graph that goes out of that node. And so the total probability of this portion, the highlighted subgraph, is going to be the total probability of this guy, which is to say the probability of aligning this portion of the input with this portion of the symbol sequence so that the last input ends up here. times the probability of this graph conditioned on this guy, right? So the probability of the entire graph is xy, or x being the blue portion, y being the red portion. It's going to be p of x times p of y given x base rule. And so it's going to be the probability of the blue subgraph times the probability of the red subgraph conditioned on the blue subgraph. What does that mean? The probability that the alignment of this portion of the input lies within this red subgraph, given that the alignment of this portion of the input lies within the blue subgraph. So are these two terms making sense? This guy is a red subgraph, this guy is the blue subgraph. Making sense to all of you guys? Yes or no? Okay. And now something simple happens. Some simplification happens over here. If you consider the total probability of all paths in this subgraph, that only depends on the node probabilities, right? And does the node probability at any node depend on the alignment of the earlier portion of the input? Not really. Look at how the recurrent network computes outputs. It processes the input at each time. It computes a recurrent hidden state. And then the output probabilities are computed from the recurrent hidden state. So this probability distribution that's computed, say, at time 3 is not at all influenced by which symbol you derived or sampled from this distribution, because the recurrence is at this level, and the sampling from this output distribution doesn't actually affect the computation of the recurrent hidden value over here. Is that making sense? When would it actually begin to affect this recurrent guy? When would it actually affect it? Can anyone tell me? When would it actually affect it? That would happen if whatever you sampled from here was fed back. Because what you obtained from here is affecting this probability distribution. Under no other condition is the actual sampling from this distribution going to have any influence on what is computed here. Is that making sense? Okay, sure. Are all of you guys okay with that? Yes or no? Okay, I'd like to see 10 yeses at least, so I can continue. Thank you. And so here's what happens. Over here, I can say that this probability distribution over here, the second term, which is the probability of the red subgraph conditioned on the blue subgraph, this conditioning doesn't really matter, because what happens over here doesn't affect any of the probabilities in this portion of the graph. And so, that's a construction of the graph, right? The point is, within this subgraph, you can start either here or here. And so, as a result, we end up with this conditioning goes away. And so now we can rewrite the whole probability as simply the probability of this red subgraph times the probability of this blue subgraph. And this guy, we will call it's the red subgraph which ends at this node, and the blue subgraph, which is the portion of all paths, is the subgraph of all paths that begin from this node. And so the total probability of the highlighted region is going to be the probability of this guy times the probability of this guy. That making sense? Yes or no? The rest of you guys, can I see more yeses? Okay, and I'm going to call this the forward probability, and I'm going to represent this as alpha TR. And alpha TR is the probability of all paths, total probability of all paths starting from here and ending at the node at the in the rth row at time t. This portion, I'll call this the backward probability. I'm going to represent it as beta TR. Beta TR is the total probability of all paths that start from the rth row at time t, but don't include this node itself. So you get what these symbols are? Yes, no. Okay. And so let's see how this works. So for this first, let's see how we can compute this forward guy, alpha TR, right? Alpha TR is the total probability of this portion of the graph. All paths that start from the source node and end up at the rth row at time t. But there are only two ways of getting to this node. One is from here and one is from here, correct? And so, is this making sense? That there are only two ways of coming here. Okay, and so what does that leave me with? It tells me that the total probability of all paths that come from here and end up here is the total probability of all paths that start from here and end up here. And then from there, you transition to this guy, plus the total probability of all paths that start from here and end up here. And from there, you transition to this guy. Is this making sense? This one? Rest of you guys, that making sense? Okay. And what is the total probability of all paths that start from the beginning and end up at symbol B at time 2? What is this one?
I have a question, sir.
Yes.
So essentially, what you're saying is that each of the paths to like the guy YIY3 is an extension of the paths from to Y2B and YB2 and YIY2, and because of that, like the likelihood, the total likelihood of all the paths to this guy will be like the total likelihood of all the paths to YB2 times like the probability of like times the probability between YB2 and YIY3 plus like the same applying to YIY2.
That's correct, right? And so what is this term? What is the total probability of all paths that end up here? Anybody? What is that? Or maybe this is more obvious. What is the total probability of all paths that start from here and end up here? If the total probability of all paths that start from here and end up here is alpha, IY3, then what is the total probability of all paths that start from here and end up here? Can you tell me? Come on, guys, that's easy. It's forward IY2, right? And so that's all it is. You're going to see that this guy is alpha IY3 is simply alpha B2 times YI3 plus alpha E2 times YI3. Is this making sense? Right. Or more generally, for any node TR, the alpha is simply the sum of all the alphas of the parents of TR times YTSR. Is this making sense?
Oh, so if you extend the probability by is the probability of the guy that comes no. The way you extend the probability is with the probability of the thing itself, YIY3.
Mm-hmm.
I see.
So is this making sense to you guys? This one here. Yes, no, I see a single yes. What about the rest of you guys? Any questions? Because we're going to use this. Okay, so Victor, where did I lose you?
Just quite confused on how this is calculated.
Okay, so here, I'm looking at the total paths, probability of all paths that go from here to here, correct? Yes, and so this is being called alpha E3, right? Yes? Okay, so now I can get to E3 either by going to B2 and then going to E3, or by going to E2 and then going to E3. So these are the only two ways of getting to E3. You agree with me? Yes. Victor? Okay. So this is basically the probability of ending up here and this symbol. And then, of course, plus the probability of ending up here and this symbol. Is that making sense, Victor? And this, the probability of ending up here, we're not worried about how you got here, just ending up here. That's simply alpha 2b. The probability of ending up here is just alpha 2e, right? That makes sense, Victor? Okay, and so just writing it down, alpha 3e is just this guy here. Compacting it, it's the sum of all the alphas of all the predecessors of 3e times y3e, or more generally, for any, let's give you a symbol. So for any tr, alpha tr is the sum of the alphas for all the predecessors of tr times ytsr, or the probability of the node. So now is this making sense to everyone? Yes or no? Okay. And so that's all it is. And so here's what we do. We end up with a alpha tr is the sum of the alphas of all the predecessors in the previous column times the probability of the node. And so in our case, every node has only two parents, t minus 1r and t minus 1r minus 1. So it's the sum of alpha t minus 1r and alpha t minus 1r minus 1 times ytsr, right? So how does this work? You can compute this for the entire graph in one shot. So initially, in the first column, you're only allowed to begin from here. So alpha for this guy is going to be the symbol probability itself, which is just y b0 over here. You're not allowed to begin from here, so the alphas for these guys are 0. Is this making sense? This first column. Okay. Subsequently, all I'm going to do is to go forward one column at a time. And in each column, I'm just going to use this simple probability formula where for each node, I'm going to sum the alphas for all the predecessors and then finally multiply by the probability of the node. I do that going down. Here in this case, this guy has only one parent, but this guy has two parents, right? So having computed the probabilities for the second column, then I can go to the third column, use the same formula. For each node, I'm going to sum the alphas of all the parents, of which there are two, and then multiply by the node probability. So I get the alphas for all of these guys, and then for all of these guys, and so on, till I get the alpha for every single node in the table. Is this making sense? Is this algorithm clear to everybody? I'd like to see a few more yeses. Okay, very easy, right? Nothing complicated at all. And so this was the forward algorithm. And by the way, so the alpha out here is the total probability of all paths that lead from B to E and align to B phi. So what do you think this guy is? What is alpha at this node? The alpha at this node is the total probability of every possible way of generating B phi. Correct? Yes or no? So that's simply going to be the probability of B phi. Making sense? Okay. So far, so good. We're on track. And so we figured out how to compute the forward probability, which is what we call alpha TR. So I'll just replace this by alpha TR. Now let's focus on the second term, which is this blue graph, which is the total probability of all paths through the blue graph, which is all paths that lead out of TR, in our case, E3, right? So it turns out that looking at just this portion of the graph is a little untidy. So you know what we're doing? The total beta TR is the total probability of this subgraph, but not including this node. You consider the edges going out, but not the node itself, because the node has been considered in the forward path. So is this clear that this is what beta TR is? Yes or no? This making sense? Guys, give me a yes, no. I see one yes from Felix. What about the rest of you? Okay. And so this is what we want to compute. But then ignoring this node makes it a little complicated. So you know what? I'm going to also include this node and call this beta hat tr. And I'm going to compute a probable and design an algorithm to compute beta hat tr. And then afterwards, I can get beta tr from beta hat tr by simply dividing out the node probability at the node. So is this making sense what I'm doing over here? I'm actually going to compute the probability for the entire subgraph, including this node, and then remove the node probability to get the portion of the graph without the node. This okay? Okay, all right. And let's see how we can do this. Once we decide this, here's what we have. Let's consider beta tr for this guy, right? Because you're multiplying probabilities all along the path around. So anytime you want to eliminate the node, you have to divide because it has been multiplied in. That answer your question? Right, yeah. And so let's look at this. What is the total probability of all paths that go from here and end up at the final node? This node has only two children. So either you can have this node and then go from here to this node, and you can have the total probability of all paths from E4. So YE3 times the total probability of all paths from E4 to the end. Or you can go from YE3 to YF4, and then the total probability of all paths from F4 to the end. So is this decomposition making sense? What we just did? And what is this guy over here? This symbol. What is this probability? Over here, we're computing beta hat E3, right? So what is the total probability of all of these guys, of this portion of the graph? What is that? Anyone? Beta hat E4. And what about this one? What is this? Come on. You want beta hat F4, right? And so, of course, all that means is that this guy is going to be, the beta hat E3 is going to be, or 3E as I've written it, is going to be YE3 times beta hat E4 plus beta hat F4. Is this making sense? This one? Exactly, right? It's like the forward, except the source and sink are switched. Easy, right? It makes sense, and it's very clear. There's nothing complicated about it at all. Any doubts so far? Did all of this make sense? Why stop at YE? Because that was the final node, right? That was our entire graph. Sure. Charlie, that answer you? Source is where you start from, and sink is where you end up at. So here, this would be the source, and this would be the sink, right? And so here's what we've got. In general, the beta hat at any node is the node probability times the sum of the beta hats for all of the children of the node. This makes sense? Yeah. And so very easy, nothing complicated, right? It's just obvious. And so now I have an algorithm to compute betas for everything. I can start off at the final column, and I say beta hat. I'm not allowed to terminate in any of these nodes. These nodes are not part of the graph. So the beta hats for these guys are all 0. And the beta hat for this guy is just the node itself, right? So it's YE8. So is this final column making sense? The fact that you're allowed that all paths must end here means that you have a beta hat only for this guy, but not the rest of them. And then once you have that, you can just go backwards, and in each column, you can multiply the beta hat. You can compute the beta hats for all the nodes in the column, and the beta hat for each node is the node probability, YTSR, times the sum of the betas for all of the children of that node. So, Hajar, that's because every alignment must begin here and end here. So which means that these are not going to have, there is no path which ends up over here. That answer your question, Hajar? Right, and so the algorithm clear to everybody? So, okay. And so once we compute this beta hat for this column, you can go back and compute it for the previous column and the previous column and all the way to the beginning. And so in one fell swoop, going all the way back, you got the betas for all the nodes in the graph. And so in a forward pass, by the way, this gives us beta hat. You actually want beta. So once you compute beta hat for every node, you divide by the node probability of the node to get the betas. You okay with this? Okay. And so we're done. This is the entire backward algorithm which computes the betas for all the nodes in the graph. You first compute beta hats, and then from those you compute the betas. And so this backward probability beta TR is computed using the backward algorithm. And so now the total probability of this entire subgraph that goes through the node TR is going to be the product of alpha TR and beta TR. So this clear? Okay. Now the thing is, what we want is the probability that a randomly sampled path goes through this node. And that term must sum to 1 over these 4 nodes. If you just take the product of alpha TR and beta TR, will those sum to 1 over these 4 nodes? Remember that alpha TR over here is simply the probability of BF, right? So they won't. So how can you make them sum to 1? How can you make them sum to 1? Scale, right? How by what? You normalize. And so we're going to down each column for every term, you're going to compute the product of alpha TR and beta TR and divide by the sums of the products. And this is going to give you the probability that a randomly sampled path goes through the node. Is this making sense? What about the rest of you guys? Felix says yes, Ibrahim says yes, the rest of you? R is just the row, right? Okay, so someone said no. What was the doubt? R, remember we said these are the rows. R represents the rows of the table. S of R represents the symbol in the row. We said we introduced this in the last class, Aditi. You remember? Summation is you're summing down this path. So you would have an alpha and a beta for each node. So you're going to compute the product of alpha and beta for each node in this column. But this product is these products, when you sum over all 4, are not going to sum to 1. So I'm going to divide by the sum to normalize them to 1. So any other questions? R not equal to R prime. Yeah, this is because the summation, that's all. When I'm doing a summation, all I'm saying is if I want to compute this term for this node, then that's proportional to alpha and beta at that node. And so the denominator is just the normalization term. So I just used a different index to not confuse it with this guy. Okay, Hiro, that answer your question? S over here, the large S is the symbol sequence BF. This is what you're given. Abel, did that answer you? So R prime is everything. You're normalizing over the entire column, right? So you'll be summing all of these. So if I have 3, 4, and 2, and I want to normalize them so that they sum to 1, I'm going to do 3 over 3 plus 4 plus 2, right? and then 4 over 3 plus 4 plus 2, right? And so that's when we sum to 1. That's what we're doing. So any other doubts? No? Okay. So this I'm going to call the posterior probability gamma TR. And so here's how the whole thing works. The divergence is the sum over all time minus of the sum over all time and a sum down each column at each time of the product of the posterior probability of the node times the log probability of the node, but the posterior probability is simply the gamma. And so this divergence is what we're going to have to minimize. So here's your third rule. Okay, 10 seconds, guys. All right, I'm going to stop it right here. First statement, true or false? Is this first statement true? What about the second one? Both of them are true, right? And so here's what we did. We computed we constructed the reduced table from the table of probabilities. And from this, we computed an expected divergence. But from that expected divergence, we want to compute the derivatives of that expected divergence with respect to every one of these probabilities in each column. Now, which means you want this vector of derivatives of the divergence with respect to these probabilities. This is what we need for backprop, right? So you guys good with this? Yes, right? Okay. Now, if a symbol doesn't occur over here, what do you think the corresponding derivative here is going to be? 0. On the other hand, if a symbol occurs twice, what do you think is going to happen? You're going to be adding the entries, the divergence contributions from both these guys, right? And so, beautiful. You're ahead of me. So I have this divergence, which is the sum over all times, sum over all the columns of gamma times log y. I have to take the derivative and get these derivative terms from here. They're going to be 0 for all the symbols that are not in the compressed table, in the target output sequence. For the rest of them, I'm going to be adding the terms of, for example, for E, I'm going to be adding this guy, gamma times log y, for all the entries that include y, but then log y is common. It just comes out, right? And so it's just going to be the summation gamma tr times log y, because this probability is common for both. You guys good with this? Yes or no? Okay. And so let's see how this works out. And this, you want the derivatives for both these guys. At each time, each location, you want a derivative with respect to the y of gamma times log y. So what is this? The derivative of gamma times log y with respect to y is gamma over y plus the derivative of gamma times log y. This you get from your high school calculus. So you guys good with this? And so this is easy. But what the heck is this guy? This is really challenging to compute because the gamma itself is a fairly complex function, right? So what is S0? Where does S0 show up? S0 would be B, right? Okay. So this guy is really complex and it's going to be very hard to compute. When something is very hard to compute, what is the usual solution? The lazy man solution. What would you do? Ignore it. Just get rid of it. Pretend it doesn't exist. And so that's exactly what we're going to do. Why is the derivative of dy s0? Where did I say s0? I don't see an s0 here. Do you? The gradient. I don't see that anywhere. These guys are the derivatives of the divergence with respect to the probabilities assigned to each of the symbols in the vocabulary vector. We have many of them. That's all. Some will be 0, the rest must be computed from here. This is what we want, this is what we want to compute, which means we need to compute each of these guys, right? And so we're just talking of how to compute those guys. There will be 0 if the symbol doesn't occur here. If it does occur, then you're going to have to compute it from here. And that means you need the derivative of gamma log y, which is gamma over y plus the derivative of gamma times log y. The second term is ugly, so we're going to ignore it. And it turns out that ignoring it is actually perfectly valid if we think of this whole thing as a maximum likelihood estimate. And if you're interested in knowing why that's okay, post on Piazza and maybe I'll answer. And so here is what happens. The derivative of the divergence with respect to any, oh, come on. Oh, shit. Oh, I'm sorry, I seem to have successfully killed my slide. How did that happen? Okay, can you guys see the slides? Okay. The mysteries of Zoom. And so, oh God, I'm way behind. So I'm going to have to fly a bit, okay? And so it turns out that this, if you look at the derivative of the divergence with respect to any symbol over here, that's going to be -1 over the probability of the symbol times the sum of the gammas for all the nodes that include the symbol. Earlier, when we were just looking at the best path, we didn't have this term. Now we just have this additional term. That's all there is. Okay? So are you guys good with this formula so far? You're not able to see the full screen? Okay. Stop share. Let me see if I can. This better? Okay. And so here's the overall training procedure. Given an input and output training sequences without alignment, first you set up the network. Typically in LSTM, you initialize all the parameters of the network. Then in each pass, you pass over the data and compute all of these probabilities. Then for each training instance, you compute this reduced probability table, compose the graph, perform the forward and backward algorithms to compute the alphas and betas. From the alphas and betas, you compute the gammas. From the gammas, you compute the derivative of the divergence for the output vector at each time using the formula that we just saw earlier, this guy, right? And then subsequently you use, which is this one, right? The derivative of the divergence with respect to yt is going to be the derivative of the divergence with respect to the probabilities assigned to each of the symbols at time t, which is 0 if the symbol doesn't occur in the graph, or it's going to be minus of the sum over all the rows in which the symbol occurs of gamma tr for the row divided by the probability itself. And then once you have this divergence derivative, you can backpropagate it and update parameters. And so this is our connectionist temporal classification framework. Story so far: sequence-to-sequence networks which irregularly output symbols can be decoded through greedy decoding, which assumes that a symbol is outputted each time and merges adjacent symbols. They require alignment of the output symbol sequence for training. This alignment is generally not given. So training can be performed by iteratively estimating the alignment and performing time synchronous training, or it can be performed by optimizing the expected error over all possible alignments. And here you need posterior probabilities, which can be computed using the forward-backward algorithm. So is everybody good with this so far? Any questions? Any questions? So what do you mean by this? Not escape all of this by passing the output of each stage to the next one. There's no output, right? We don't really know what the output is. We just get anytime you pick a unique output, that's like guessing an alignment, right, Hajal? So we're trying not to guess. So we've gone through most of it, but then we are still left with two problems. The first is a key decoding problem, which we mentioned early in the last class. Consider the problem where the output symbols are characters, and I have a decode where I just greedily pull all the most likely symbols, and I get read. Is this the word read or is this the word read? Can you be sure from this guy? Yes or no? No, you cannot, right? So you cannot distinguish between an extended symbol and repetitions of the symbol. There is a problem. And so we are going to solve this by introducing an extra invisible symbol in our vocabulary, often represented by a hyphen or a blank, but it's not really a blank. An invisible symbol is a symbol that is just not seen, but is actually a symbol. It's a separator. So for example, it's part of your vocabulary. So if your alignment is RRR, blank, 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 EE, blank, 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 DDD, and then you use the previous strategy of just collapsing repetitions, these three R's become an R, these three blanks become an invisible symbol, a single invisible symbol, but it's not seen, so it's not here. These two E's become an E, these three D's become a D. And so this becomes red. Is this making sense to you guys, what we just did? This one, right? And so similarly, this one, these two will collapse to R, this collapses to E. Here, these two E's are going to collapse to an E. This stays a D, so this becomes read. This making sense? And what would this guy become? The two R's become an R. Then you have an R again. The two E's become an E. You have a D. Then the two D's become a D. It's double R, E, double D, right? So what is this one over here? What would this become? Anyone? What would this become? Triple R, double E, triple D, right? And let's check if you're right. That's exactly what it is. So you get this. Beautiful. And so now here's your fourth pole. Ten seconds, guys. Okay, and end this right here. Can someone tell me the answer? Which ones are valid expansions of Billy? Anyone? What is the answer? Just D, right? So what does this become? What does this become? This just becomes B, I, Ly, right? This is going to become B, B, I, L, L, Y. This is going to become B, I, L, Y. Only this becomes B, right? So clearly you get the idea. And so this is what happens, right? But then this, how do you use this blank? The blank now is an extra symbol in your vocabulary. You're going to get an extra row of probabilities corresponding to the blank symbol. And now if you did a greedy, inference on this, if you got something like this is going to become B, E, B, right? Very clear. You're sure that these four Fs are a single F because you're allowed to collapse things. The invisible symbol works as a separator. Now, what would this become? Anybody? What is this? Over here. If you got this as a greedy decode, what would this be? Anyone? What's this one, guys? Did I lose you? Is the class still here? Hello? Beefy, right? What about this one? What is this? Anybody? What is this? Double FE. So beautiful, right? And so this works. But then you have to change our training strategy and how we compose graphs. Earlier, when we didn't use the blanks, this is how we composed a graph. For example, if I had eddy with two Ds, if I composed a graph like this, if I looked at a best path through it, I couldn't distinguish between EDY and EDD. There's between a double D and a single D. So to deal with blanks, now we're going to see things slightly differently. So I'm using Beefy as an example. Here, this arrow means there's a connection from beer to E to fur to E, right? So if I use blanks, this graph shows you every way of composing a Beefy using my symbols because the blank is an invisible symbol. Burr can be immediately followed by E, or it can go through an invisible symbol and be followed by E. And in both cases, it's going to appear as B. Is this making sense? Over here. Right? Similarly, E can either be immediately followed by F or go through an invisible symbol. It doesn't matter because the invisible symbol is invisible, right? Now, on the other hand, if I have eddy, then can be immediately followed by D or go through an invisible symbol. But D cannot be immediately followed by D because if it is, anything of that kind, the two Ds will get collapsed. It must go through the invisible symbol. Is this making sense? Right? And so that's a simple change. That's all we do. And so now, if I want to compose my probability table for eddy, here is the graph for eddy. I can have an initial blank because it's invisible. Then I must have an A. I can have a blank or go and then go through the blank through to D, or I can go straight to D. From D, I must go through a blank and then to D because the two symbols are identical. Then from D, I can either go through a blank to E or go directly to E, and then this final blank is an invisible symbol. This is also possible. And so this is the table. Is the table making sense? Is this making sense, guys? To all of you guys? Right? Clear, right? And so if I draw the graph, here's what it's going to look like. See the arrows on the left? So I always have horizontal arrows. Then I have diagonal arrows because from any symbol, I can go to the symbol immediately following it. But if the symbol, non-blank symbol, if in any row, if the symbol two symbols away is identical, then I cannot skip the guy in the middle. Because if I skip it, they can get collapsed, right? But so the simple row is from every symbol, I'm going to draw a diagonal row down. And if the symbol two rows away is not the same as this guy, then I also have an arrow going down like this. And that's going to give me the graph for this guy. Is this making sense to everybody? Yes, no, what about the rest of you guys? Is this making sense? Okay, and so that's it. So now I have composed this graph. Observe that I can either start with a blank or with the first symbol. I can either end with the final symbol or end with the blank. And every path through this graph, every path is going to be an alignment of eddy to the input, guaranteed. A valid alignment where the repetitions are properly dealt with. And so thereafter, again, skips are allowed in general. You're allowed to skip a symbol if the two symbols on the either side are not the same. And if not, you're not allowed to skip a symbol. You can apply it to every row of this table. And so now the forward-backward algorithm, if the next symbol is the same, okay, because if I had this graph, if I had this arc, then I could just produce A, D, E. Right, Matt? Yes or no? And if I collapsed repetitions, what would it become? If I collapsed repetitions, what would this become? It's just going to become 80, right? Do we want that in this case? So over here, the blank is mandatory, right? All right, and so now the forward graph, we're going to make the alphas for all of these guys 0, and for these two nodes alone, the alphas are going to be the node probabilities. Then you follow the same rules as before, where as you keep going across the table, at each node, you multiply the node probability by the sum of the alphas of the parents. And similarly for the betas are 0 for all of these guys. For these beta hats, they're going to be the node probabilities for these two guys. And then as you go back, at each node, you multiply the node probability by the sum of the betas for all the children. The algorithm itself did not change. Only the nature of the graph changed. So this clear to everyone? Okay, and posteriors and derivatives are computed exactly as before, but with the extended graph with blanks. And so the overall training procedure is as follows. You're going to have the input, your model is initialized. At each time you're going to compute a probability vector. And so, you're not given alignments. How do you train? You set up the network, you initialize the parameters of the network, you compute the probability vectors, including the probabilities for the blanks. And remember, the blanks are implicit. It just happens, okay? You don't need to explicitly mark the blanks. Anytime there's a repetition, there's an implicit blank. And just by the nature of having some training instances where you have repetitions, you have automatically included a blank in your target sequence. And then, of course, you set up the graph, you run the forward pass to compute the alphas, the backward pass to compute the betas. You can compute the gammas from those. And then from the gammas, you can compute the divergence derivatives as before and back propagate them to our mini batch and perform your training. So the overall framework we saw, called this connectionist temporal classification framework, is called the connectionist temporal classification framework and applies to models that output order aligned but time asynchronous outputs. Is this clear to everybody? Any questions? Any questions? No? Why don't we add a blank only before the repetition sound? The point is the blank is an invisible symbol. So you want to treat this the same everywhere, right? If I think of the blank as an invisible symbol, I've just added an invisible symbol. That's all. One more symbol. And so because it's invisible, it can occur anywhere. It's mandatory in some places. So, all right. So final thing, remember that we performed a greedy decode by picking the most likely symbol at each time and merging the repetitions. But this is in fact suboptimal because it finds the most likely time synchronous output, which is not necessarily the most likely order synchronous sequence. So let me give you an example. Let's say read this. I have 6 input vectors, and I've considered these 6 alignments. These are the total, all the alignments I can pull out of my graph. So this collapses to red and has a probability of 0.7. This is a different alignment, which also collapses to red and has a probability of 0.68. This guy collapses to, has 0.69. On the other hand, for TED, this alignment has a probability of 0.71. These two guys, the other two guys, have probabilities of 0.3 and 0.29. If I pick the most likely alignment, I'm going to pick this guy. But if you were to consider this entire set, which do you think is a more reasonable choice? Red or TED? Red, right? Because it's robust to variations and alignments, and this guy is not. So in fact, what we really want to do is to compute, the compressed symbol sequence which has the highest probability across all alignments. Now, remarkably, greedy decodes work just fine in these models, right? And the reason for this is this. This is from the original paper by Graves. They find, guys, I'm going to go a couple of minutes over. Please bear with me because we had some issues. It turns out that the nature of the problem is that the blank symbol probabilities just pop up whenever transitions happen. And so if you just perform a greedy decode, you often end up getting perfectly reasonable decodes. I'm not going to go over this because we're out of time. But what we really want to find is the order aligned sequence that is most probable, which means I want to consider all possible sequences of any length up to the length of the input and to find the one which is most probable. And for this, I'd have to search through this guy for every possible, I'd have to compute the probability of the order aligned sequence for every order aligned sequence and pick the one that's most likely. And we know how to compute the probability of an order aligned sequence. You can just compose this graph for the order aligned sequence, and the alpha out here is going to be the probability of the order aligned sequence. So this alpha here, for example, is the probability of B phi. So you'd have to compose this graph for every possible output and then run the forward algorithm and pick the output for which the alpha was highest. Is that making sense? Yes or no? Right. Do you think it's feasible? It isn't feasible, right? But that's the theoretically correct thing to do. And so the actual decoding objective is to find the most likely asynchronous symbol sequence. Here's a poll. I'm not going to actually post it, but actually, can you tell me if the first statement is true or false? The actual objective of decoding is to identify the compressed sequence that has the highest probability. This is the same as finding the compressed sequence with the highest forward probability, true or false? Also true, right? Both are true. So how do we do this? We can't do this explicitly. So we're going to organize all possible symbol sequences in a semi-tree. What do I mean? So let's say I have only two symbols in my vocabulary, S1 and S2. Implicitly, I also have the invisible symbol, the blank. So the first symbol can be a blank. It can be an S1 or it can be an S2. So you can either start with a blank and go to S1, or start with a blank and go to S2, or directly start with S1 or with S2. No problem. Now, S1 can be followed by S2 directly. S1 can also be followed by S1, but for that you have to go through an invisible symbol. And S1 can also be followed by S2 through an invisible symbol. So this shows every possible way of constructing a two-symbol sequence that begins with S1. Is this clear? This shows every possible way of constructing a two-symbol sequence, right? Same thing down here, right? S2 can be followed by S1 directly or through a blank. S2 can be followed by S2, but it must be followed through a blank. This shows every possible way of constructing a two-symbol sequence that starts with S2. And then I can just continue this tree. From each S1, I can be followed either by S1 or S2. Each S2 can be followed by S1 or S2, and so on. This tree represents every possible way, every possible symbol sequence that can be generated by the network. Is this clear? Yes or no? Okay. And so here's what I'm going to do. This tree is what I have out here on the vertical axis. This is the horizontal axis. And now observe that every node in this tree represents a unique sequence. This node represents S1, S1. This node represents S1, S2. Although there are two ways of generating S1, S2, this guy is invisible. This node represents S1, S2, S1. This one represents S2, S2, S1. And so if I construct this graph where I have edges following these arrows, then every node over here represents a unique symbol sequence. And then I can just run the forward algorithm through this guy. So is this graph making sense to you guys? Over here. I see one yes. What about the rest of you guys? I just followed this graph, this tree, and unrolled it into a graph, right? Yes, X is time, yes. And now I can just run the forward algorithm to compute alphas, except this tree keeps growing exponentially. When the tree grows exponentially, what is its common solution? Standard solution. We should be done in a minute, guys. What is the standard solution when something grows exponentially? Anyone? Okay. Remember, the forward algorithm. So again, for this guy, the total probability of B phi is going to be the sum of the alphas for these two nodes. So for any symbol, anyway, hold that aside. What we can do is start off initially, compute alphas for all of these guys, but then we can use a beam search where we only retain the top k, expand only those guys out, retain the top k, and keep going forward. And when you run out of inputs, you're only going to have a small number of alpha terms over here, and then you pick the symbol sequence with the highest alpha, and that's going to give you the proper alpha-based decoder. Does this make sense? I don't see any responses. Okay, so I have a whole bunch of pseudocode for this. Obviously I won't go through this. So the story so far, just adding to what we saw, distinct repetition of symbols can be disambiguated from repetitions representing the extended output of a symbol sequence by the introduction of blanks. Decoding can be performed through best path decoding or through but optimal decoding based on the application of the forward algorithm can be performed through a tree-structured representation of all possible output strings and a beam search. And so I have some extra slides, but that comes to the end of today's lecture. We'll continue with sequence-to-sequence models of other kinds in the next class. So I'll stop the recording right here. Thank you for waiting the extra couple